Okay, hello everyone. We are starting a new topic, magnetism. This is more like the second part of this course, electricity and magnetism. So we talk about electricity in the first 8 weeks. Now we are switching to magnetism and related topics. So let's see what are the different sections we're going to discuss. So we'll talk about magnets and magnetic fields, how electricity is produced using magnetic fields. Now here's something interesting. So far we talk about using electric batteries, so chemical reactions to produce electricity, right? Now we're going to use a totally different concept, a totally different idea. Magnetism. We use magnetism to produce electricity. And with that, how the force going to play a role in magnetic fields, how force acts on charged particles that are moving through magnetic fields. So there's so many good applications in this behind this concept. So we'll talk about practical applications like that. Things related to motion, torque, force times distance. You should remember what torque stands for. Talk about that, and some practical applications, some mechanical devices like motors, how they work, all related to magnetism and electricity. Some other instruments like things that we use to generate sound, measuring devices like galvanometers. We'll talk a little bit about electron, uh, something called the Hall effect, very important when it comes to magnetism. Mass spectrometer. This is something you use in your chemistry lectures or chemistry related research. How this thing works, what's the working principle behind it. So these are some of the topics we will be discussing. Okay, all right, let's move on. So most of the first few slides pretty much a self-study. I will go briefly over them. I want you to go back to your textbook and read the relevant paragraphs, get some better picture, better idea. But let's go briefly over this. Magnets have two ends. We call them two poles. We call them poles. We call them north and the south pole. Like poles repel, unlike poles attract. Kind of similar to electricity ideas, right? The electric charge. We know that negative repel, negative positive attract, like charges repel. So it's the same thing. If you think about a piece of magnet, a bar magnet, you might have seen one for sure. It's a piece of iron, piece of metal. Certain metals have magnetic properties. An easy example is iron. Iron can become magnetized. So when you have a bar magnet, it has two poles. We say the north and the south pole. It doesn't need to be a bar like this. It can be something like this, a U shape or a horseshoe magnet. Again, north and south. The property about magnetism is like poles. Like if I have two magnets like this, north and another magnet facing north, south here, there's a repulsion between them. Like poles, they try to push each other away. If you bring opposite poles towards each other, like this, now here north, here south, there's an attractive force between them. They try to attract each other, right? So that's how they work. Like poles repel, opposite poles attract. Okay, so let's move on. However, if you cut a magnet in half, you don't get a north pole and a south pole. You get two smaller magnets. So, the other thing. Let's say you want to isolate a north pole, or you want to isolate a south pole. What if you cut this thing in half? Do you get something like this? A piece of metal with one pole, one north pole, and nothing on this side? Doesn't work like that. The moment you cut it, it creates a south pole over here, and this piece will have a south and a north here. You keep cutting, you are making smaller and smaller magnets, right? So as of now, so far, we haven't identified single poles. Here's that's one difference between magnetism and electricity, or magnetic poles and electric charges. Electricity, you can have single poles, a positive charge or a negative charge, like an electron. These are single charges, single poles, right? But in magnetism, it always comes in pairs, north and south. Okay, let's move on. Magnetic fields can be visualized using magnetic field lines, which are always closed loops. So this is a simple activity or a demonstration we can do in the class. We try to picturize the magnetic field line. So we say that when we have a magnet, north and south, there's some kind of field exist due to these two ends. And to represent that, we use magnetic field lines. And we say that field lines start from the north pole, goes into the south pole. So this is how we draw magnetic field lines. Starting from the north pole, going into the south pole. The density of field lines is higher near the poles, right? Everything starts here. So there's so many poles starting here. So that's why the magnetic field strength is greater near the poles. So same thing over here. Whatever the number of field lines leaving the north pole, the same number has to come to the south pole. And they have this curve-like shape, and you can trace them easily. You place a magnet on the table, and then you take a compass, a bunch of them, place them here and there randomly, and you see that these little pointers, they all align along the field lines. Another thing you can do is take a magnet, put a piece of paper on top of it, like a white piece of paper, and here's the magnet, and then sprinkle some iron dust on it. And if you look at them from the top, if you look at it from here, here's a person. Okay, you will see something like this on this picture, the colorful picture. They will align along these magnetic field lines. So these are simple proofs that to show that what these magnetic field lines look like. Remember during electricity discussions, so let me erase this. We draw electric field lines between charges, like positive and positive. We draw them leaving the positive charge, and in between pushing them away. It's the same thing when it comes to magnetic fields. So let's say there's a north pole and a south pole here, this magnet, and you put another north pole and a south pole here. The field lines are leaving the north pole, back to the south pole. Same with this guy. In between, they're gonna push each other away, creating a empty blank area in the middle. So I want you to give a try drawing these things for south pole and a south pole, north, south, all these combinations, magnetic field lines, these diagrams. Okay? Alright, let's see what else we have. Magnets and magnetic fields. Earth's magnetic field is similar to that of a bar magnet. You already know this. Planet Earth, our Earth, has a magnetic field. And the diagram shows it appears like a bar magnet inside the Earth. There's not really like a physical bar magnet inside. Note that the Earth North Pole is really So here's a little research question for you. I want you to find out what's the source for this Earth's magnetic field. What creates it? There is no real bar magnet inside, but there is something that generates this magnetic field lines. It is very important that we have a magnetic field. Some planets don't. Having a magnetic field is really, really crucial to the life on Earth. So here's the second research question. Number one, why, like how do we have a magnetic field? Like what creates it? Number two, what are the advantages because of that? Like how it supports life on Earth. Okay, so going back to this, so the magnetic south is in the North Pole, magnetic north is in the South Pole, and it doesn't really align with the Earth's rotation axis. It's little shifted to the side to one side, and it's not fixed. It changes very slowly. Like I believe current prediction is in about 10,000 years this can change significantly. It's slowly changing the alignment. As of now, we can use a compass to find the North Pole approximately. The North Pole of the compass points towards the South Pole because it gets attracted to the opposite pole, so that way we can find roughly where the North Pole is. Okay, so moving on. The uniform magnetic field is constant in magnitude and direction. The field between these two wide poles is nearly uniform. So if you want to create a uniform magnetic field, we have to have like a large wide two magnets. Remember, we create electric fields. We have two metal plates, one positive, one negative, and there's an electric field between them. Same way, if you want to create a magnetic field, you need to have two large magnets. We keep North Pole here and a South Pole here, so the other end is over here on the other side. So I'm not going to draw the other end of the magnet. So here's a North Pole, here's a South Pole. There is a strong magnetic field between. Electric fields we denote with the letter E. Magnetic fields, what's the letter we use? You can guess, a good guess will be letter M, but unfortunately we don't use that. The magnetic fields are denoted by letter B. Okay. Alright, electric currents produce magnetic fields. Before that, I want to go back and add something to this. So the second diagram, you see there's a North Pole and a South Pole, magnetic field lines, and like this. You see these little lines here. These things are called magnetic domains. A domain is a small region within the bar magnet or within the magnet, right? So these are like tiny little magnets, microscopic size little magnets. So each domain, if you magnify it, it's also like a little bar magnet. These are regions where couple of atoms showing the same magnetic property. Where is the magnetism coming from? Like the origin of magnetism in a metal or in a some piece of magnet. It's the motion of charged particles. It's the motion of electrons and protons. Electrons, they move around the nucleus, right? So they have motion. Protons, they're kind of fixed inside the nucleus, but they have something called the spin. You can think about it as kind of a little rotation. So these movements are the reason for magnetic field, right? A charged particle by itself, if it is stationary, it wouldn't create any magnetic field. All it has is electric field. But a moving charged particle can create magnetic fields. So it's the movement of these charges what gives rise to the magnetic fields. A magnetic domain is a small region where all those charged particles, most of them kind of align in the same way. So they have a net magnetic field. Now, let's say you have a piece of iron that is not a magnet, just a piece of iron. It's not magnetized. Now, if we examine this microscopically, we see these tiny little domains align in random directions. So, because of this randomness, that's how the nature is, or the alignments are usually random. They cancel out their own magnetic fields. Individually, one piece has a magnetic field in one direction, this one has the magnetic field in this direction, this one pointing this way, like that. They cancel out each other's magnetic fields, so statistically the net effect is zero. We can magnetize a neutral piece of iron. What do we do? There's a couple of ways to do that. Probably some of you might have done this. You take a magnet, so you have to have an actual good magnet. You take a magnet, let's say the North Pole, and you drag this over the surface of this neutral piece. So you drag it a couple of times in the same direction. You keep striking it a couple of times using a magnet, right? So this is a non-magnet, initially non-magnet. This is a magnet. Take the good magnet and you kind of slide it over the non-magnet a couple of times, 20-30 times. So what happens is this North Pole or the magnetic field of the good magnet will slowly align all these little domains in one direction. Now it sums up, they all add up, and then you have a good strong magnetic field in one direction, right? So that way you can make a magnet out of a non-magnet. Now, why do we need certain materials like iron, cobalt can become magnet, nickel, and their combinations? Not every material can become magnet. So in these particular metals, once you align them, they can retain this alignment for long periods of time. In most metals, in most materials, they go back to their random directions immediately. They won't retain this alignment. So that's why you can't make magnets out of everything. Only certain materials have this ability. Okay? Alright, let's go back. And again, all these mostly self-study kind of stuff, so please read and find out more information. Electric currents produce magnetic fields. Alright, so here's an interesting theory or a concept. Electricity can produce magnetic field. I told you guys that moving charges create magnetism. So if you have a, let's say, a conducting wire, a copper wire. So there's atoms inside, there's electrons, atoms, everything inside. They all have their tiny little magnetic fields, but usually they're in random direction, so there's no net magnetic field. But if you connect this to a battery, let's say you put a battery like this. Now we know that there's a current flow in this, so the current over here is going up. What is a current? Current is motion of charged particles, moving charges. Now this wire can become a magnet. It will be a temporary magnet. It will be an electromagnet. The magnet created by electricity. That's an electromagnet. This magnetic field around this wire has a particular shape. How do you find that? We have something called the right hand rule. So you take your right hand. Now we are trying to find the direction of the magnetic field or the shape of the magnetic field around this wire. Now let's call this A, B. So A to B is our conductor. And over here B, C, D, E, B to C, C to D, that's also conducting wires. We're not going to worry about the magnetic field of the other pieces. Let's just focus on A to B. Alright, this piece, the one that, this highlighted piece. So you take your right hand. So, and this is your right hand. You place it over here around this, and you bend your fingers like shown in the diagram. Direction of the thumb, you place the thumb in the direction of the current. Now the thumb is pointed in the direction of the current. When you do that, the direction shown by these fingers that are wrapped around the conductor, that's the direction. It shows how the magnetic field lines around this conductor. So they're going to be little circles going around the conductor, right? So throughout the length of this conductor, this is A to B conductor, has these little circles of magnetic fields along the length, right? So since current is going up on the left side, this is the left side of the conductor, this is the right side. The left side, the magnetic field is coming out. It's like coming towards you. We indicate that by a circle and a dot inside. That tells you the magnetic field, or whatever the field we are talking about, is coming out from the board. It's coming towards you. On the right side, just take a pencil or something, put your fingers around it and see which way the fingers are pointing or rotating. On the right side, it's going into the board. So that's a cross and a circle. That tells you that the direction is into the board. Okay. So that is right hand rule. There's another right hand rule. So this is one of the right hand rules, the first right hand rule, just to show the direction of the magnetic field when there's a current in a conductor. All right. Okay. So moving on. So what are we doing here? So we have this conductor. Now, if it is a straight wire like this, current going up, you know that it's going to be little circles of magnetic fields like this. It's stronger closer to the wire. It gets weaker and weaker as you go away from it. Now what we're going to do is we take this wire and we bend it into a circle. Right? So imagine something like this, a circular piece of wire with a battery connected. So there's going to be a constant current going in a loop. Every point, consider every point, you place the right hand, you put the right hand here, the right hand rule tells you that the magnetic field is coming out over here, going in over here. I will show this in class also on video. So by following throughout the loop, at every point you try the right hand, you see that it's coming out like that. So that's the same thing in the picture over here to your right. So by bending a wire into a circle, you can actually create a stronger magnetic field, because all the magnetic field inside the loop is in one direction, all the magnetic field outside the loop is in the opposite direction. So inside the loop you have a much uniform, stronger magnetic field. So how do you make it even stronger? You make multiple loops, a coil out of it. That way you can create a much stronger magnetic field inside. Okay, force on an electric current in a magnetic field. Alright, so this is where actual equation starts. So I will discuss this in the next video. Okay.